All right, I'm back. So, one thing I forgot to mention to you is that I would like you to calculate the power. I calculate the resistance out of each bulb, but also calculate the power drawn by each bulb. All right. So, remember I'm imagining by the time I'm doing this early, but I imagine by the time we get to this lab, we will have talked about electrical power, and that for a light bulb represents brightness. The brighter the bulb, the more power it draws. The more power it draws, the brighter it's going to be. And remember, power is current times voltage used, energy used, current I times delta V, or I squared R. Um, so P equals I delta V, which is equal to I squared R. It's also, or if I substitute in Ohm's law, then I can get the fact if I substitute in for I can also get that power is delta V, um, delta V times delta V is delta V squared over R. Okay, that those are just these two equations, Ohm's law and the power equation, Joule's law, put together. Anyhow, so notice how bright this is all by itself. Oh, you can't even see it. Sorry. So you see how bright that is by itself. Now these are two identical bulbs. When I connect the two identical bulbs in series, what do you think is going to happen to the brightness? Think about it for a second. So I'm going to connect them in series. The charges are going to run into it's a series circuit. So it's going to run into the resistance of this bulb and the resistance of that bulb. You have increased the resistance overall in the circuit in series. All right. Do you remember that resistance is proportional to length? And this is like doubling the length because they're identical resistors, or identical bulbs. So if you've doubled the length, you haven't changed the overall voltage from here. If this is 1.5 volts, and that's 0 volts, then this would be at 1.5 volts, and that would be at 0. So the voltage available, the energy available is the same overall, but you've increased the resistance, and so you've dropped the current. You've increased the overall resistance. The voltage for the whole circuit is still 1.5 volts. You increase the current. In this case, because they're identical, you've doubled it. So you should have about half the current. That would be half the current going through the entire circuit, half of it going through here. So if the current, to make up a number, if the current were 4 amps originally, then now I only have 2 amps going through each bulb individually. So if I have less current going through each bulb, then I'd expect it to be dimmer. Not only that, but they have to share the voltage. You only have 1.5 volts available. This is going to get some of it, and that's going to get the rest of it. All right? The voltage, remember, you go from 1.5 volts to 0, and so this is going to use up some of it, that's going to use up some of it. So not only has the current been reduced by half, but the voltage available to each bulb has been reduced by half. And so we should see that you can hardly see this. You can see that they're still lit, maybe barely. Can you see that? They are lit, but hardly, because there's so little. So it's gone down. The power's gone down by 1/4, half the current, and half the voltage available for each one. The current's been reduced because we've doubled the overall resistance because they put in a second bulb in series, and they're identical bulbs. So twice, it's still 1.5 volts coming out of here, but twice the resistance, half the current going through the entire circuit. But on top of that, 1.5 volts, which means that this is going to get half the voltage, 0.75. Yeah, 0.75. And that's going to get 0.75. So half the voltage and half the current. So the reading for the current now is, let's see here. I'm not getting a current reading. Dang it. This thing. Oh, there we go. The current reading now is 0.173. 0.173-ish. Okay, through the whole thing. And the voltage over this whole thing. So I'm going to measure the voltage from this side to that side. It looks like these things are not identical, but they're pretty close though. So from one side to the other, the voltage is 1.44 for the entire thing, 1.44 from that side to that side. If I do just the first bulb, we find the voltage over just the first bulb is about 0.7. It's jumping around. 0.69, 0.7. Let's just call it 0.7. 0.7. About 0.7 amps. This one should be about the same also. Again, it doesn't look like they're identical. But well, it doesn't matter. It should be about the same also. Yeah, it's about 0.7. Okay. That's the potential, the voltage. This one's about 0.75. The other one was about 0.7. And this one is a little bit brighter. So they're not perfectly identical. Again, this was about 0.75-ish. This one about 0.7, 0.69. The voltage dropped on this first bulb. All right, so that was about voltage. Voltage dropped about 0.69. That was about 0.75-ish. Okay. The current is still right around 0.17 through both of them. Remember, the current's the same. So the current comes out the battery, goes through here, goes through that bulb, goes through that bulb. It's the same throughout. Now, here's something I want you to really note. I'm going to disconnect the second bulb and put in a long bulb. So now, this is the round bulb, and that's the long bulb. You know that from what we did in the very beginning, the round bulb, I asked you to calculate the resistance, and it has less resistance. That's why it's brighter. It's brighter because it has the same voltage, 1.5 volts, but it draws more current. And so if it draws more current, it's going to be brighter. The same voltage for both bulbs, 1.5 volts over this. One that draws the more currents, the one with the least resistance, and that's going to be the brighter bulb. So this is the brighter bulb, the long bulb is the dimmer bulb because it has more resistance. But now I'm going to put them in series. Round bulb, long bulb. And what do you think is going to happen? Which bulb's going to be brighter? Now remember, now they both get the same current because they're in the same series circuit. They get the same current, but they have different resistances. Which one's going to be brighter? By themselves, we know the round bulb is brighter and the long bulb is dimmer. But when you put them in the same circuit, I hope you can see that. This is the long bulb. Here's the round bulb. It's not even lit. That's the one that was brighter all by itself. It is working. Yeah, it's broken. No, it's not. If it were broken, if I just lift this up and disconnect the circuit, then the whole thing goes off. I'm just lifting this up so that the metal's not touching. All right, so the long bulb goes up. When I touch it, that bulb goes on. So there is current going through this bulb, but it's got less resistance. Small current, but smaller resistance. The power is so small that it's not even lighting. It's not even glowing. These bulbs are based on heat, and it's just not hot enough to have a byproduct of light. So this one lights up. Now let's do this in parallel. Okay, and let me see, how am I doing on time? I'm going to stop this and rearrange this thing so we have a parallel circuit right here, and I want to talk about that. Okay, so I'm going to stop this one, and I'll see you in a moment.